Okay, in this video we're going to start looking at what's inside the nucleus. So, inside the nucleus, as you may already know, those of you who are smart cookies will remember that there are protons and neutrons inside of the nucleus, and that the charge of a proton is plus 1e, and the charge of a neutron is just 0. And that's going to have important consequences for some of the observations we see later on. So, what's inside of the nucleus? We've got protons and neutrons, so let's just zoom this bad boy in. So we've got our protons and neutrons. Okay, so we'll start off with the protons. I've drawn them in red here, so we've got a proton. So what's a proton made out of? Ever asked yourself that question? Well, a proton is made out of 3 quarks. 1, 2, 3. And those 3 quarks, there's 2 of one and 1 of the other. One is an up quark, the other's an up quark, and a down quark. So we've got 2 ups and a down. And that makes a proton. Why does that make a proton? Well, quite simply because these quarks have properties. An up quark has the property of plus 2/3 of a charge E, and a down quark has minus 1/3 of E. And hopefully those of you who are a bit more math savvy will look at this and go, yeah, of course that makes sense, because we've got 2/3 here plus 2/3 there, so that gives you 4/3. To make 1e overall, we need to get rid of a third, so we've got minus a third there. So we can add those 3 values together and we get 1. And that makes sense, we get positive 1e. So, how do we make up a neutron then? Well, a neutron is also made up of 3 quarks, but it's made up of a different set of 3 quarks. What 3 quarks would you think it was made out of? Have a think, see if you can work it out. From those, it's definitely ups and downs, there's nothing else in there. See if you can work it out. Well done if you've already worked it out, if you were able to think it through. The correct answer is up, down, down. And let's have a look at the numbers that go into that. So up is plus 2/3, down is minus 1/3, down is minus a third, so 2/3 minus 2/3, what do we get? 0. And so we have the charge on the neutron. And that's effectively how we make up our quarks. Because quarks are a fundamental particle. They are the smallest thing that we know exists. When we break things down past the atomic level, into the subatomic level, down to protons and neutrons, we can now say what protons and neutrons are made up of. And we say they're made up of quarks. And in this case, as we've said, up, up, down, and up, down, down. For all intents and purposes, it actually doesn't matter whether you call this down, up, up, or up, down, or down, up, down. As long as you have the right number of quarks, the order does not matter. So that might answer that question for you there. So what other kinds of quarks have we got? Well, we've got quite a few other different types of quarks, and we need to introduce you to all of them for your specification. So, as we've already mentioned, we have up quarks and down quarks. And we represent that with the letters up and down. But we also have a third type of quark that you need to know about, and that is the strange one. And that's represented by the letter S. Now, quarks, as you know, all have very distinct and important properties, because that's what allows them to make up the things we need in terms of protons and neutrons. And we'll have a look at an example of how we utilize strange quarks later on as well. But we've got up quarks. Now they have a charge, as we've already said, of plus 2/3 E. Down quarks minus a third E. Strange quarks, they follow a down quark charge. They have a minus a third E. Well, there is something else to be considered here, because they have something called, quarks have something called a baryon number. So once upon a time when you were first told about charge, you were like, what the heck is charge? Well, you now know what charge is. We've identified charge and it has a number. And we've gone through our lives accepting that charge is a thing. Well, quarks also have another property called a baryon number. I'll write that at the top here. Baryon number. And that baryon number is specific to each quark. And guess what? It's nice and easy to remember because all quarks have the same value, which is, guess what? A third. So the baryon number of these quarks is a third. Unfortunately, there is another thing, because at the moment, you can see here, this is the up quark and the down quark and the strange quark. Between the up and the strange and the up and the down, we can tell the difference. But what about this one? Look, it's got a charge of a minus third, charge of a minus third, baryon number of plus a third, baryon number of plus a third. So really, at the moment, there's nothing differentiating these two quarks. Well, there is, because a strange quark has strangeness. And we're going to talk about that now. That's another property that quarks can have. Strangeness. I know this sounds kind of weird and odd, but yep, strangeness. Mostly, these words are used because of the properties that they exhibit when they're a part of whatever particle they are. So we're going to talk about some strange particles that, as you would surprise, as through no surprise of here, they have strange quarks that make them up because they have strangeness. So up quarks, they're not strange at all. They're 0. Down quarks, they're not strange at all either. 0. Strange quarks, however, have a strangeness of -1. Unfortunately, there's no nice, easy way of remembering that. You've just got to remember that strange quarks are that way round. They are -1 strange quarks. But just to add to that confusion here, we need to appreciate the fact that there are other types of quarks as well. There's not just up, down, strange. There's also charmed, bottom, and top. You don't need to know about those 3 other types of quarks. The only ones you need to know about for this specification is up, down, and strange. And unfortunately, they have variations within these. So the up quark, there is an anti-up. An anti-up quark is represented by U bar. Anti-down quark is represented by D bar. And guess what? Anti-strange is represented by S bar. So that's quite an odd set of quarks to introduce, and they are anti-quarks. They're opposite of these in every other way possible. That's the nice thing about anti-quarks. If you know what the normal version is, so like up, you can work out what the anti-version is just by doing whatever the opposite is. So in this case, the antiparticle of up has a charge of minus 2/3. Make sure that's a minus. Same thing for anti-down, plus 1/3. Same thing for anti-strange, plus 1/3. What do you think the baryon number is? You guessed it, minus 1/3. Minus 1/3, minus 1/3. What about the last column, strangeness, then? What about the last strangeness column? Well, Opposite of 0 is just 0, so unfortunately there's no strangeness there. Same thing with a down quark. What about an anti-strange? What's the opposite of -1? Hopefully you're thinking +1. Great job, well done. +1. So an anti-strange quark has a strangeness of +1. So these are all the quarks and the properties you need to know now. Now, one thing I will point out is that these are quantities that need to be conserved. They need to be conserved because when we do reactions where quarks are going to change, we are going to see those changes. We need to make sure that any changes that occur, there has to be a balancing of properties on both sides of the equation. As you would always expect, there's always conservation when these reactions take place. So those are all our different types of quarks. So quickly, I'm going to go into the categories that quarks fit into. Now, everything that quarks make up is called a hadron. All these things are just words, okay? So just bear in mind these are names. So if you were learning someone's name for the first time, you'd be learning their name. You'd try and memorize it. Same thing with this. Hadrons are anything that's made up of quarks or anti-quarks. And those split into two very distinct categories. Okay? The category we've already seen and we're quite comfortable with is the baryon category. Well, you might be thinking, well, hold on now. I'm not sure. I've never heard that word before apart from in that table. Well, believe it or not, you know all about baryons because baryons are things or particles that are made up of 3 quarks. Can you name a particle with 3 quarks? Yes, you can. Protons and neutrons. So protons and neutrons form part of the baryon classification of hadrons. Remember, hadrons are anything that's made up of quarks or antiquarks. And so we have a baryon that's made out of 3 quarks. We can obviously also get anti-baryons because we can have 3 anti-quarks. So, for example, you can get an antiproton. Let's draw a picture of an antiproton as an example here. So, if a proton has up, up, down, then an antiproton has anti-up, anti-up, anti-down. And what's interesting about this particle is that you can quite nicely see, well, anti-up is -2/3, so -2/3. That's at -2/3. But anti-down is +1/3. Add all those together, what do you get? -1. So in terms of the charge of an antiproton, we have a total charge of -1 because it's an antiparticle of the original. So instead of having to go, well, an antiproton has a charge of -1, we now know why it has a charge of -1 because the anti-version of a proton has an anti-up, anti-up, anti-down, which are all antis in their own right. So you will have noticed that baryons have a baryon number of 1 because each one of these is going to add up to 1/3. So this one's a -3, -3, -3, so he's going to have a baryon number of -1. So baryon number equals -1 in this case. Obviously for a normal proton, we'd have a baryon number of +1. Have a look back at your table, have a look at the previous page where we kind of explained the structure of a quark, and hopefully that will come together. So a baryon, such as a proton, has a baryon number of 1. The anti-baryon, in this case antiproton, has 3 antiquarks making it up, so has an anti-baryon number of -1. So, okay, so that's the first category there, baryons. Now, there's another category that you have not come across before, or it's unlikely that you've come across. That is mesons. Now, mesons are very, very peculiar because mesons always go around in quark, anti-quark pairs. They never ever go around in quark-quark or quark-anti-quark pairs. Now, the nice thing about mesons is that hopefully you'll be able to realize is that if they're only made up of a quark and an anti-quark, then the baryon number of a quark is plus a third. The baryon number of an anti-quark is minus a third. So they have a baryon number of 0. Hence, they are not a baryon. I'll say that again. A quark has a baryon number of a plus a third. An anti-quark has a baryon number of a minus a third. So when you add those together, because they go around in a pair, the total baryon number of this particle is 0. And so as a result, this is not a baryon. Hence, it's a meson. It's a lovely way of thinking about it because even though it's made out of quarks and the way baryons are, the baryon number of a quark-anti-quark pair always equals to be 0. Hence, they're not a baryon. Okay? Unfortunately, there's no meson number that makes this a bit easier, but that is just the way it is. Okay, so in the next video, we'll probably look at some more examples of mesons and baryons and the ways in which we can utilize these. We'll start looking at some more advanced kind of variations and also another type of fundamental particle which we'll come across, which is leptons. So that's to look forward to.